All right, guys, so today we are going to chat about the idea of these trig functions, and um, we're going to actually see that they're what we call circular functions. So if we add 360, right, or if we're at 0 degrees, and we do one full revolution, we're back at 360, and if we do another one, we're back at the same place. So the idea here is that if we look at sine, cosine, and tangent as functions, okay, so remember what a function is. For every input, there's one and only one output. We see that we have some repetition once we do a full revolution. Okay, so what we want, we want to start thinking about the trigonometric functions. And I guess we've talked about these being trig functions before. Hold on, my pen here, just a second. Okay, so these trigonometric functions, I don't know why there's a lag in my writing here, that's all right. We want to think of these as, remember, functions have domains and ranges, and what we want to think of with these trigonometric functions, we want to think of our domain now. Our domain used to be an angle, right? And that's okay, we can kind of still think of it that way. Where we have our domain being angles, but now we're not only going to think about them in angles, we're also going to think of these inputs as just real numbers. And it's hard to get your mind to start thinking about this in terms of real numbers and not angles, because the whole definition of the trigonometric functions, right, is that we talked about them being ratios of sides of triangles, and that's when we talk about these angles. But what we actually want to think about now is that we can actually input any real number, and when we talk about those real numbers that we are talking about are radians. They have no, like degrees, right, have a unit on them. They're degrees, whereas now we have these real numbers and we just want to talk of it as radians, and those radians are just those real numbers, okay? So recall that we have defined theta, right, to be S over R, or another way to think of that if we solve this for S. So what if I multiplied, hold on one second. Sorry if this video seems kind of choppy. My computer isn't quite doing what I want it to, but okay, so recall that we had theta equals S over R, where S is that arc length, right, of a sector of the circle. But what if we're on the unit circle? So on the unit circle here, I should probably not use black. There we go, that's better. I don't have that lag like I was having before. So on the unit circle, we know that x squared plus y squared equals 1, right? That's the formula for a circle that is centered at the origin with radius 1. And on the unit circle, if we have radius 1, so let's just look at, oh man, I'm gonna just have to draw circles for you guys today because I don't have my, that's not a circle. Pretend that's a circle. What do I know? I know this distance right here is 1, right? I know this would be my theta, and then this is what we call that arc length. So in this case, if I have theta equals S over R, in the unit circle, I know R is 1, so actually theta is just equal to S. And so when we're talking about the angles going in, if you notice now, my theta is actually just equal to the length, basically an arc length. So even though this probably isn't going to really change the way you think about how to do these, because when I show you examples of how to find like sine and cosine and tangent of radian values that are bigger than 90 degrees, I even still think of it kind of as an angle. But what I really want to kind of point out for those of you that maybe are going to be math majors someday, I'm so excited for you, by the way, this right here is just a real number. It doesn't actually have any units to it. It's not a degree. And so look at what we've shown, that on the unit circle, we know that theta is equal to just a real number. And we also know that this can be true for not just a unit circle, but we can find all of our sine, cosine values of just of any of these real numbers now. And we can be on the unit circle because it doesn't matter what radius circle we actually have. We'll get the same thing. So on the unit circle, let's talk about this a little bit more, and this is going to lead to our discussion of eventually how to find sine, cosine, and tangent using the unit circle. if you want to memorize the unit circle, and if you've had trig before, you probably know what I mean by that. I am not going to require you to memorize the unit circle. You can actually do all of this with that chart of values that you already know, right? With the 30, 45, and 60, you just have to switch it to radians. But so for a unit circle or a basic circular functions, okay, so let's define a couple of things here. So for a real number s, and that's the key here, is that that real number, it's not, we don't want to have to think about it as an angle anymore, that determines a point let's just call that point xy, okay, on the unit circle. So let me go back to my horrible picture here for a minute. Okay, my horrible picture. So on this picture right here, when we're talking about that xy, we're saying that this right here, that is my coordinate xy. Okay, so this s right here is this distance, and this s right here determines a point on my circle, and we're going to call that xy. Okay, so that's what we just mean by determining a distance. Okay, oh, I was on the wrong layer. Man, today's just, I don't know. Okay, xy on the unit circle. Then we have the following. So if I take the sine of, so again, remember here, if I take the sine now, I'm not just taking the sine of theta. Theta is equal to s on that unit circle. So I'm actually taking the sine of s now, and not necessarily the angle. That's just going to be, if we look back here, same idea, though I still want to think of this as, I still want to think of sine, right, as if s is equal to theta, and this is the point xy, then this is x and this is y. So look at what sine would be. Sine would be opposite, which is y, over my radius, which in this case is r. So we have kind of a new definition for sine now. We're talking about not just sine, cosine, and tangent also. But if I'm on my unit circle and I do basically y over r, but r in this case, oh yeah, you guys probably saw that coming. It's just my opposite angle, it's just my y values. So if I'm on the unit circle and I know I have a point on the unit circle and I want to find the sine of that real number, right, that is that distance, that arc length, or if you want to think of it as the angle, you can think of it as the angle. It's just my y coordinate. Cosine then of s we know is x over r, but on the unit circle, right, r is 1. And then tangent of s, right, is y over x. Okay, then of course cosecant of s is going to be 1 over y. A couple things here. Right here, it'd be in poor taste if I didn't state that x can't be 0. So tangent is, and looking at it this way, if you look at the x equals can't be 0, then you know right away that tangent is undefined on the x-axis. Okay, secant of s is 1 over x. And right here, y can't be 0, of course. So that means cosecant is not defined on the y-axis. Excuse me, on the x-axis. When y is 0, that's the x-axis. And right here, when x is 0, this is the y-axis. I'm so sorry. This right here is the x-axis. And then secant 1 over x, x can't be 0. So this, again, is the y-axis. Secant isn't defined on the y-axis because that's when x is 0. Notice that tangent and secant have kind of the same restriction, that x can't be 0. We're going to see that tangent and secant kind of have some special things together. We're going to have an identity that they're going to share. And actually, if you get to calculus, you'll see that secant and tangent have some similarities when we look at like derivatives. Also with cotangent and cosecant. If you don't know what a derivative means, don't worry, but it's exciting. You're going to know someday. But cotangent and cosecant, if you see, are undefined when y is 0, so they can't be on the x-axis, or we can't define them when we're on the x-axis. So that's kind of some of the stuff that's interesting about this. But those are our new definitions, and if we're on the unit circle, the nice thing about that is you can just say, like, okay, what is the sine of this? Well, it's just the y coordinate of that point, right? That arc length, or think of it as the angle, that's fine, through which it goes through. Now, let's look at then how we actually figure out these points on the unit circle, and let's talk about how we can find these values if we're given the unit circle. So I'm going to just attempt to draw a circle. I'm nervous about this. Okay, so there's my y-axis. There's my x-axis. Oh, you guys. Man, I really need something. All right, guys, that's the best I can do. I made a little stencil and I tried to trace it out on my computer, and you know, we'll just see how this goes. So I'm gonna cut this guy in two, and then another two, putting it on the XY axis. Sorry, that's not perfect. Okay, but this is so this is of radius 1, and what we want to kind of see is, so can we figure out some of the points on the circle that correspond to some of these s values that I want? So for example, let's look at pi over 3. Actually, let's start with pi over 6. Yeah, we could do pi over 6. So let's look at pi over 6. So pi over 6, right, is about 30 degrees. And again, I can think of that as a real number now. There are my 3 that I know, right? I kind of know pi over 3, pi over 4, and pi over 6. I'm sorry, excuse me, pi over 6, pi over 4, and pi over 3. And so I can figure out, if I can figure out the coordinates for this point right here that corresponds to, if I had an angle, right, of 30 degrees, what would that point right there be? Well, I know that this is 1, right, because this is of radius 1. And what else do I know about excuse me. What else do I know about triangle? If I drew that triangle, this is 30 degrees here. So remember we talked about that 30, 60 degree triangle at the very beginning. We kind of looked at, we took like an equilateral triangle and figured out all the sides and stuff. And so what we have found, and this is true with any 30, 60, 90 degree triangle, is that the shorter side is always half the hypotenuse, and then the longer side is always root 3 times the shorter side. Okay, so this is just true for a 30, 60, 90 degree triangle. So what do I know then? I know that this point right here is root 3 over 2, comma 1/2. Okay, so look at, there's my x value, there's my y value, and that just comes from the fact of what I know about a 30, 60 degree triangle. Let's look at if we can fill in maybe any of these other ones. Maybe I don't just know 30. Okay, so let's look and see what would happen with 45. So 45 degrees, right, would be right about here. And if I come straight down here, so this is going to be my pi, this is pi over 4, right? And I know if this is 1, right? So I know, remember, so let's think about if this is 1. This is a isosceles triangle. So I know that a squared plus a squared, because the sides are going to be exactly the same, is 1. So that gives me 2a squared equals 1, which tells me a squared equals 1 over 2, which tells me that the square root of 1 over the square root of 2, or 1 over root 2, or root 2 over 2 is what these distances are going to be. So this is going to be root 2 over 2. This is going to be root 2 over 2, okay? And so I can figure out then what is the point there on the unit circle. That point right there corresponding to pi over 4 is root 2 over 2, root 2 over 2. Isn't that great? And look at, so what does this mean, you guys? So this guy, this one right here corresponds to pi over 6, right? This one right here corresponds to pi over 4. And then really quick, let's do pi over 3 and kind of see what we're going to get there. So let me erase some of this here. So I'm just getting these all kind of set up in the first quadrant, and then we'll see how we can use this to figure out some of our values, not just in the first quadrant, but in other places also. You know, there's a lot of quadrants out there. If I look at this guy here, so I know that this is pi over 3 or 60 degrees, right? So again, if I let this be 1, the shorter side is 1/2. This is the shorter side because it's opposite that 30 degree. This is the longer side, so that'll be root 3 over 2. It's root 3 times the shorter side. And so what is the point that we get here? What is the point? That's a great question that's more philosophical than we need to get into here. My x's value is 1/2. What is my y value? that's root 3 over 2. Okay, and what does this correspond to? This corresponds to pi over 3, right? Because that's the angle that would go through that point. Or another way to think of it is that's the arc length, right? From the x-axis up to that point. That's that arc length. So based on this unit circle and in the first quadrant here, what I have drawn, right? With these new definitions that I have, I actually can figure out a couple of things, which is new for me sometimes, to be able to figure out a couple of things. And this unit circle we're going to fill in, so on your notes or whatever. But so based on my newfound definition, let's look at what sine of pi over 6 is in this case. Sine of pi over 6 is going to be the y-coordinate of that point on the unit circle that corresponds to an angle, right? I know you got to kind of think of angles or the distance, not only the angle, but also this distance here would be pi over 6. So what is the sine of pi over 6? It's the y-coordinate, which sure enough, it's 1/2. Do you see that? Yeah. And then what would the sine of pi over 4 be? Well, what's the y-coordinate corresponding to pi over 4? Root 2 over 2. And then the sine of pi over 3, if you look at the y-coordinate, that's root 3 over 2. And you guys notice that we can, if these are real numbers now, that's what we really want to stress. But I also want you to realize that these also, if you think of them as angles, it can be kind of the same thing. So pi over 6 is out, not radians, but in degrees, is 30 degrees, and we know the sine of 30 degrees is 1/2. Pi over 4 is 45 degrees. We know that the sine of 45 degrees is pi over root 2 over 2. And here, of course, that's 60 degrees. We know that the sine of 60 degrees is root 3 over 2. So before, when we found the values of like, on your exam, you had, values that weren't just in the first quadrant. We had values that were all over. So how can we find values that are not just in the first quadrant, but that are anywhere in these quadrants? Okay, well, let's look at how we would think about this in angle terms, and then we'll talk about how to do this not in angle terms. So let's talk about reference angles again. So let's look first at this idea of pi over 6. Let's say if I am pi over 6 away from the x-axis, because that's what a reference angle is. Either here or here I could be pi over 6 away, right? Or here. Remember, reference angles are pi over 6 away from the x-axis. So what I want you to notice really quick is that if I consider these points, really all they are, you guys, are reflections. So if I consider this point, whoops, that's not what I wanted to do. Don't get rid of my beautiful circle. If I consider this point right here, which is pi over 6 away from the x-axis, this point right here is actually just a reflection about the y-axis. So what do you notice is the same with this point? If you notice, these points are both the same distance above the x-axis. So that means that my y value here must be 1/2. It's the same height, right, as this point right here. And then what do you notice? It's actually almost the same distance, right, from the origin. It's just on the opposite side. So how do I describe that? Well, it's the same distance from the origin, but on the opposite side, this would be a negative root 3 over 2. So again, same point, right, other than I have a negative root 3 over 2 because it's on the opposite side. Same thing down here. If you notice, this has the same x value, so it's still going to be a negative root 3 over 2. But now I'm just going to flip it down to the bottom, so it's a negative 1/2 because it's in the third quadrant. And then finally, this point right here with reference angle pi over 6, right, it's going to be same x value because I'm in the fourth quadrant. My x is the same, but I'm in the fourth quadrant. That means my y is negative. So notice those points right there. Anytime you give me or you ask me to find, like let's say I want you to find the sine of 5 pi over 6. So the reference angle here is going to be pi over 6. I'm going to give you a little bit of a hint here. Your reference angle, I shouldn't say all the time, but pretty much all the time, is just going to be pi divided by whatever your denominator is there. So 5 pi over 6, that means we're pi over 6 away from pi, right? This would be 6 pi over 6. So 5 pi over 6 is a pi over 6 away from pi. So that means we're right here. Okay, I hope that makes sense. If it doesn't, let me know. So what is my y value? Whoops. What is the y value for that point right there? It is 1/2, so it should be 1/2. What about the sine of 7 pi over 6? That's 1 pi over 6 away from 6 pi over 6. So that's going to be this guy right here. So that's going to be a negative 1/2. And I could do cosine also. I'm just doing sine for right now. Let's look at some of the other values or some of the other angles. I'm going to tell you right now this section is going to have to be two parts. It seems like that's what these sections take a long time. And I am totally okay with these taking us, 2 parts to do some of them. That's okay. Let's look at 45 degrees. So 45 degrees, I could be here. Let me get rid of this right here. Okay, so 45 degrees, right? If my reference angle is 45 degrees, I'm 45 away from the x-axis. So I could be here, I could be here, I could be right here, right? Or I could be right here. Again, the same idea for this 45 degrees right here. If I just take that point and move it over, my y value is the same, but my x value is going to be negative. Okay, we're going to get a little squishy in here. I don't know if that's a word. Squishy is a word. So I'm actually going to move that over a little bit. So what at this point right here would be a negative root 2 over 2 and a positive root 2 over 2 because my y is going to stay the same. Here, right, I'm in the third quadrant. X and y are negative in the third quadrant. But I want to have the same x distance and the same y distance from the origin. And over here, my x's are positive in the fourth quadrant, and my y's are negative in the fourth quadrant. And that corresponds to your sine and cosine, you guys. Remember, cosine now we're defining as just your x values. Notice where are my x values negative? In the second and third quadrant, and that's my points. Look at my x values are negative in the second and third quadrant. That makes sense because we know cosine is negative in the second and third quadrant. And cosine now is defined to be those x values. There's a lot to the unit circle, and it's pretty great. Likewise, I could find some of these. So, if I wanted to find, let's do cosine now, just to mix things up a little bit. Cosine of 7 pi over 4. So think about, if you go up 1 pi over 4, you're at 8 pi over 4, which would be 2 pi, right? So that cosine 7 pi over 4 then must be right here. Okay, so what is the cosine of 7 pi over 4? What is the x value of that point on the unit circle? That's root 2 over 2. Okay, so I can use that unit circle if I know all of these. And really, if you want to memorize unit circle, which I'm going to tell you right now, I don't memorize the unit circle, and actually what I use is I just use reference angles on my chart to find these, and I'll show you how I do that. But if you did want to memorize the unit circle, what I highly recommend is just memorizing these 3 values right here, and then doing exactly what we're doing right now, where we just take, if it's in the second quadrant, then all of my x's are negative and my y's are positive. If it's in the third quadrant, I'm going to take all these guys and make them all negative. And if it's in the fourth quadrant, I'm going to take all these guys, I'm going to make my x's, keep my x's positive, and make my y's negative. All right, guys, last one. So let's look at if we had a reference angle of 60 degrees or pi over 3, right? So we have this point, this point, this point, and then this point right here. Let me get rid of some of these lines. It's a good time. I'm having a good time doing this stuff. I like doing this. Weird, huh? Isn't that weird that I like doing this? All right, let's look at this one. Remember, this guy corresponds to having the same reference angle as this angle over here. And so again, I'm gonna just change. This is gonna be a negative 1/2 and root 3 over 2 for this point right here. Over here, it's gonna correspond to this guy, except everything's gonna be negative. So that's a negative 1/2 negative root 3 over 2. And then right here, positive for my x values and negative for my y values, okay? I hope that makes sense. And now, really quick, before we finish up with this beautiful picture of mine, let's talk about these points right here. So 0 degrees, right? And I actually do think of the unit circle a lot when I'm trying to remember sine, cosine, tangent of these values on my axes, because I know that this point right here is 1, 0, right? That distance is 1. So right away I can just look at that, and if I wanted to know the cosine of 0 degrees, or of 0 radians, shouldn't use degrees, I know it's just the x coordinate, which is 1. If I wanted to know the sine of 0, it's just the y coordinate, which is 0, okay? If I wanted to know the tangent, I would just take y divided by x, all right, guys? This, likewise, this point right here is 0, 1. This point right here is -1, 0. And this point right here is 0, -1. And notice, so if I keep going around, I still have these definitions for sine, cosine, and tangent of it just being the x or the y coordinate, or a ratio of the x and y coordinate. So that's what we mean by a circular function. Because if I keep going around, what ends up happening is we just keep repeating these points on the circle, right? So that's what a circular function is. So let's look at some more examples of these, and we'll come back to, I actually want to show you kind of how I do this. That's my first layer. That's good to know. Second layer, let's get rid of that. And then I'll show you how you can do it with the unit circle also. So let's just evaluate, find the exact value. And then we'll be done. We have one more thing to talk about in this section. So probably I'll record that and get that posted also, but this one's getting a little bit long. What I want to talk about is I want to talk about the graphs of sine and cosine and tangent, and even like look at the reciprocal functions also. These are the graphs that you're going to need to know. So the graphs of the 6 original trig functions you're going to need to know how to graph without the use of a calculator. Okay. Other than when we get to 6.6, we're going to talk about how to like transform those graphs and stuff. I'm not going to have you graph the transformations without a calculator. You will have a calculator to use for that, but I just want you to know the original 6 without the use of a calculator. So let's find some function values right here, and then we'll call this good. So first one, let's find the cosine of 3 pi over 4. Okay, so I'm not going to lie to you. I don't use the unit circle when I do these. So what I like to do, and I'm going to make my chart over here, is I make my little chart. So I look at 0, pi over 6, right? Pi over 4, pi over 3, and let's just put pi over 2 because I haven't given myself enough room. And I make my chart. And then I figure this out using my chart. And I want to show you a trick for making your chart. I think I've already shown it to you though. Where you, let's redo this, Sarah. Goodness gracious. So 0, pi over 3, or excuse me, 6 is 30 degrees. Pi over 4 is 45 degrees. Pi over 3 is 60 degrees. Pi over 2 is 90 degrees. And then let's look at pi, and then 3 pi over 2 you can figure out also, right? Just by that's where I really use the unit circle, is with those guys. So let's look at sine. Whoops, should have thought this out a little bit. Why would I do that? That would make these lectures way too boring if I thought these out. Sine of theta. Let's not use theta anymore. Let's use s. You can think of it as theta though. S. So sine of s, sins apparently. Cosine of s. And tangent of s. And I could find the other ones, of course. Oh, this chart is beautiful. This is one that's going to go in the record books. So sine of 0, if I look at 0, right, on my unit circle, my y value there would be 0. Okay, so that's 0. 30 degrees is 1/2. You guys know these. I'm going to just go ahead and put these down. You should know these anyway, 1 and 0. Cosine of 1 is 0. This one, if it's not 1/2, it's the other one, right? This one is the same, root 2 over 2. This one's 1/2. Pi over 2 is 0, and pi is actually -1. And then tangent just takes sine. That's why I always put sine first. It's y over x, so it's sine over cosine, so that's 0. Root 3 over 3, you know all of these. 1, root 3, undefined, and then 0. Okay, and then we could do 3 pi over 2. But so here's how I do cosine of 3 pi over 4. So cosine of 3 pi over 4. Now, if you didn't want to do it let's first look at cosine of 3 pi over 4. Where is 3 pi over 4? That's going to be probably the hardest thing with some of these. You should get to where you don't have to change these to degrees to evaluate these. And these will be on a non-calculator part of the test. So you won't really have a calculator to verify if they're degrees or not anyway. What I want you to think about is 3 pi over 4. So look at your denominator. Your denominator is 4, so your reference angle is going to be just pi over 4. And you are 4 pi over 4 right, would be, so sometimes when I know what my reference angle is, I'm going to rewrite pi in terms of my reference angle. 4 pi over 4 would be pi. 8 pi over 4 would be 2 pi. So 3 pi over 4 is pi over 4 away from pi, okay? So my reference angle is pi over 4. So the way I figure out cosine of 3 pi over 4, I come over, I look at the cosine of pi over 4, its reference angle, and then I do the same thing that I would have done when I found degrees, right? It's in the second quadrant and it's negative. So we get a negative root 2 over 2. Does that make sense? What if I wanted the sine of 3 pi over 4? Same thing, right? I see that my reference angle is pi over 4. I find the sine of pi over 4. That's root 2 over 2. Then I think about if it's positive or negative. I'm in the second quadrant, and y values, remember sine of your y values, is positive in the second quadrant. So that would be a positive root 2 over 2. You could also do this with the unit circle. If you have memorized the unit circle, which that's a good time in and of itself, where is 3 pi over 4? You still have to, still have to figure out where that 3 pi over 4 is. So here's 3 pi over 4. Here's the point corresponding to it. So I know my y value is root 2 over 2. My x value is negative root 2 over 2. So that's going to be your cosine, and that one's going to be your sine. Okay, you will not have to fill out a unit circle for me. You don't have to memorize the unit circle. If you want to memorize the unit circle, you are welcome to use the unit circle instead of your chart. But I just find I've already had to memorize my chart. Why don't I just go ahead and use my chart to figure these out? So, whoops. Oh my goodness. So let's look at another one. What if I wanted like the tangent, let's say, of a negative 7 pi over 6. Okay, so tangent of a negative 7 pi over 6, I know my reference angle is going to be pi over 6, okay, and I know I'm going negative, so this would be a negative 6 pi over 6, right, and then this would be a negative 12 pi over 6, because I know I'm going the opposite way. So this here is 6 pi over 6's. I want a negative 7 pi over 6's, so that's going to be my negative 7 pi over 6 right there. So what's my reference angle again? It's pi over 6, right? So I come and I find the tangent of pi over 6. That's root 3 over 3. And then in the second quadrant, tangent, remember all students take calculus, tangent is negative in the second quadrant. So I get a negative root 3 over 3. Hope that makes sense. Okay, one more and then I'm going to let you go. What if we wanted something like cosecant of, I want to do, how about 14 pi over 3? Oh, this is going to be crazy, you guys. So 14 pi over 3. I know my reference angle is pi over 3, so let's see what's happening with pi over 3. This would be 3 pi over 3. This would be 6 pi over 3. Add another 3. This would give me 9 pi over 3. Right? Add another 3. This would give me 12 pi over 3, which that makes sense. That's 4 pi. And then look at 12 pi over 3. Oh, Sarah. I need 2 more pi over 3's, right? So here's 1 more pi over 3. Here's 2 more pi. So there's 1 more pi over 3. There's another pi over 3. Okay, so actually this angle is, so there's 6 pi over 3, there's 12 pi over 3, there's 14 pi over 3. But really all that matters here is knowing what quadrant I'm in and also knowing what my reference angle is. So my reference angle is pi over 3, right? I'm in the second quadrant. Cosecant is 1 over sine. So I know that it's going to be root 3 over 2 flipped. And it's going to be positive because I'm in the second quadrant and sine is positive in the second quadrant. So that's 2 root 3 over 3. Those are really fun. I really like doing those. I hope you do too. If you have any questions, of course, let me know or let Ms. Weir know, and enjoy. And I'll finish up this section and get that posted early next week.